everyone, so in this video I want to go over how to solve some stoichiometry problem involving volume and mass. So in terms of volume and to volume relationship, Avogadro's hypothesis tells us that at the same temperature and pressure, equal volumes of all gases contain the same number of gas particles. So for example, if you have 1 liter of hydrogen gas and 1 liter of O2 gas, and they are at the same temperature and pressure, they would contain the same amount of gas particles. Now furthermore, what we have is that 1 mole of any gas at standard temperature and pressure, which is 0 degrees Celsius and 1 atm, occupies a volume of 22.4 liter. Now this conversion factor is really important when we go into the problems because it will help us convert from liter of something to mole of something. Now in mass volume and volume to mass calculation, for the one I'm going to give you on the homework on the quiz, all the gases you are to assume that they are at standard temperature and pressure unless I say otherwise. Then let's get into the actual calculation. So first problem, I have this reaction here between hydrogen gas and oxygen gas, creating some water vapor. We've seen this reaction plenty of time before. Now I have a different question to ask you in terms of this reaction. What volume of O2 gas is required to completely react with 30 liters of hydrogen gas, assuming that all volumes are measured at STP? And we know STP from is standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. This piece of information, like I mentioned before, is important because knowing this information will allow you to use the conversion factor of 1 mole occupies 22.4 liter. Now, we didn't have that assumption, we wouldn't be able to use that conversion factor. So let's get into how do you actually tackle this problem. So first of all, I always start with the given. Now, I want to identify which one is my given, and 30 liter of hydrogen gas is my given. And what I want at the end is I want a volume of O2 gas. After you have identified the given and what you want at the end, you want to come up with a strategy of how you're going to tackle this problem. So my strategy actually is just converting straight from liter of hydrogen gas to liter of O2 gas. Now this is possible because due to Avogadro's hypothesis, the mole ratio that we get from the balanced chemical equation is also the volume ratio, meaning that the ratio of H2 liters to O2 liter is 2 to 1. And we get a 2 to 1 from here. This is 2, and there's the invisible 1 in front of O2. So knowing that, we can start always with the given, which is 30 liter of hydrogen gas. I will multiply that by the volume ratio between hydrogen gas and oxygen gas, which are the two things we want and given. So I put 2 liter of hydrogen gas at the bottom because I want it to cancel out. And I put 1 liter of O2 at the top because I want to keep, because we want liter of O2 at the end. So just punch it in the calculator and noting your significant figure, you get 15 liter of oxygen gas. It is as simple as that. Now another strategy actually I have is just showing you how that conversion factor, the 1 mole occupies 22.4 liters of gas, comes into play. And that's strategy number 2. So you would go from liter of hydrogen gas, convert that to mole of hydrogen gas, and then using the mole ratio to convert that to mole of oxygen gas, then using this conversion factor to go back to liter of oxygen gas. Now you'll notice something very interesting. So let me go through the calculation. So you start with your given, and now you put your conversion factor at the bottom because you want it to cancel out. And you put mole H2 at the top because that's what you want. So on and so forth. You do the mole ratio between H2 and O2, 2 mole H2 and 1 mole of O2. Then you convert it back to a liter of O2 using that conversion factor. You will get the exact same answer you notice that when you take a look at these fractions, these actually cancel out. So really, technically, when you punch in the calculator, it's just 30 divided by 2, just like how the calculation of strategy 1. Now, but this is useful to be able to understand the concept and behind this conversion factor, and why is it that the mole ratio is also the volume ratio. And this calculation shows that. This is also gets you into the good habit of using this conversion factor of the 1 mole is occupies 22.4 liters of gas for our different other problems, like the one that goes from mass to volume or volume to mass. So that's this problem. Let's move on to another example. So for this example, I'm using the exact same reaction, but I'm asking you a different question. So now my question for you is, what volume of water vapor is required to completely react with 30 liters of hydrogen gas, assuming that all volumes are measured as Cp? Now, always, of course, we want to start with identifying what is our given. And my given is 30 liters of hydrogen gas. So that's my given. And what is it I want at the end? I want a volume of H2O gas at the end. So this is what I want. So now let's set up our strategy and set up our calculation. So because it's only a volume to volume question, we just need to apply the volume ratio, which in this case is also the mole ratio that you can get from the balanced chemical equation. So here's my strategy. Going straight from a volume of hydrogen gas to volume of water vapor. So I set it up to be 30 liters of hydrogen gas. I multiply it by the volume ratio, and I get that from the balanced chemical equation. I put liter of H2 at the bottom because I wanted to cancel out, and a liter of water at the top because I want to keep it. Now we can cancel out liter of H2, giving you liter of water. So because the volume ratio is 1:1, basically your answer should be the same as your given. So 30 liters of water. Just like our previous example, we can also do the second strategy where it is a little bit longer, but it really shows how the concept behind why is it the volume ratio is also the mole ratio, like so. And you do the same calculation, basically the same step as the last example. It's just a little bit of a different mole ratio and a different unit of chemical. But you should get the exact same answer at the very end. All right, that is it for the volume to volume calculations.